Hello friends, welcome back to the lab, HDL lab 18ECL58. So you already seen how to use your Xilinx software. I hope so. You also checked upon how to download, and I hope you have started executing on your own in your homes. So moving ahead, with the hope that you have started practicing, today we'll touch upon the next experiment, and the next experiment is regarding your 8:3 encoder with priority and without priority. Okay, but one small rule here is what now, friends? It should be with behavioral description. It should be with behavioral description. So you can just observe here, friends. This is a syllabus copy which was mentioned. Okay, so if you can observe here, he has told clearly that 8:3 encoder with priority and without priority, but it should be in behavioral model. He has specifically defined in the syllabus. It has been specifically defined that it should be in behavioral model only. So therefore, we'll try to do the programming in behavioral model itself, like how we did your 2:4 decoder. If you had observed your 2:4 decoder, it was in structural model only, and it was using only NAND gates. Similarly here, he has not specifically told which gates has to be used and all those things, but he has defined that it should be in behavioral model only. Okay, so we'll just try to do it now. So this is your 8:3 encoder, what you can see here in the figure. The theory behind it and the logic behind it, you might have also studied the logic and theory even in your DE classes, that is digital electronics, as well as you might have also studied this in your HDL theory classes as well. Okay, so moving ahead, I will not be touching upon these things, that what is the logic, what is the theoretical logic behind this encoder. I'll just touch upon the programming logic. Okay, so to give you a short introduction, it has 8 inputs and 3 outputs. Apart from that, an enable pin will be there, which is an optional. Sometimes we consider this enable pin and sometimes we don't consider it. So this is an encoder. Whatever the truth table you can see right now, it is an encoder without priority. Here I have considered the encoder without priority. In the next case, we will consider it with priority. Okay. So if you see the first case here, enable is 0. You can see the enable is 0. And when the enable is 0, it means that all our inputs are don't care and the output would be 0. Next, when the enable becomes high and when one of the input becomes high, then all of the outputs would be going to 0. Okay, that means what now? Input 0 is being donated by all the outputs as 0. Okay, next is your input 1. When the input 1 is high, it means that the first one is high. So therefore you can see here 0, 0, 1 and so on. So when the 7th input is high, it means that a 7 is displayed, indicating that the 7th input is high. So this is the logic behind your 8:3 encoder without priority. There will be no priority in this. The next case, what we'll be seeing is it will be with priority. That we'll see in the next half. So for this, we'll be writing the Verilog code. Along with the Verilog code, we'll be also writing the test bench. Okay. So let us see first how the Verilog code will look. Okay. So this I have already written. Fine. So if you can see here, this is my Verilog code. The name of my Verilog code, I'll just try to zoom it out. I hope so it's visible now. Okay. So this is our Verilog code. You can see the name of my Verilog code is what now? Encoder 8:3. Next, how many inputs are there? There is one enable, a single bit enable. Next, there are 8 inputs. So therefore, we have used it in the form of a vector. You can see there I have written 7 down to 0. It means that totally 0 to 7. That is 8 inputs. Okay. Next is how many outputs? There are 3 outputs. That is 0, 1 and 2. So therefore there are 3 outputs. So that's why we have written here 2 down to 0. The same thing must also be defined in register. Why? Because we are using behavioral description. I hope you know that the keywords in your behavioral description are register and always. So it's very mandatory to use these two keywords, register and always. So that's why we use the keyword here, reg. Okay. So you can just notice, friends, I have made a small changes in the writing style. Earlier in the previous code, we have written all the inputs first in the bracket here. We had written a bracket, inside that we had written all the inputs, and then we had written a program. But here I have made a small change that directly I written the inputs, I have closed the bracket and I have finished the module. So you can just compare the previous code with this code and try to find the differences, and we'll also check out whether this code is executable or no. Okay. So I hope this part is clear. This is the name of the module. These are my inputs and this is my output, wherein I have written everything inside the bracket here. Fine. Next. Next thing is, friends, the keyword which is very important in your behavioral description is always at. So we are using it always at asterisk mark. What is the meaning of asterisk mark now? All the inputs. Asterisk mark means that all the inputs, which are my all the inputs? Input in and input en. So this is one way of writing. The other way is, you might have studied in your theory classes, you can directly mention the inputs. The inputs here are what now? En and in. You can directly mention them. No problem. Okay. Next. So begin. After begin, just observe this statement, friends. If not of enable, that is, if not of enable, then output is 0. That means if enable is equal to 0, then what would happen now? Not of enable means enable would become 1. That means at that time the output will be 0. It means that the enable pin which I am using in my code is active low. Is active low. Is that clear, friends? So you can try it out active high. The code I have written here is active low. As an exercise, what you can do is you can try with active high enable. Just think out, you can get active high enable and write the code. Okay. So in this case, when my enable is 0, then it would be negated and considered as 1. At that case, my output is 0. That means all my outputs are 0. That means we are trying to do this condition, the first condition. When my enable is 0, the output is 0. So this condition is satisfied. Okay. And you already know, friends, if I am writing a behavioral description, it will be nothing but based on your truth table. That's why I have shown you the truth table already. Okay. So here you can see, friends, this is my input. So this is my concatenation sign. We use the concatenation sign. Why the concatenation sign is necessary? Because here there are 8 inputs. We should concatenate all the 8 inputs. That's why you use the concatenation sign. The concatenation sign is nothing but this flower bracket. Whatever the flower bracket you can see here, it is a concatenation sign. Okay. Next thing. Next, this is nothing but a copy of your truth table. Whatever you can see inside this case statement, it is a copy of your truth table. That's all. Like say, for example, the first combination, it is 00001. That means input 1 is high. Okay. So you can just observe here. When the input 1 is high, that is line 0 is high, the output is 000. All the outputs are low. So that's the same thing what we have done here. When the input 1 is high, all my outputs are 000. Similarly, when the line 1 is high, then the output is 1. When the line 2 is high, the output is 2. When the line 3 is high, the output is 3, and so on. When the line 7 is high, the output is it could be 6, or you just modify it to 7. So when the line 7 is high, it should be 7. Okay. So you can just see from the truth table. Okay. When the line 7 is high, all my outputs are high. So the same thing we have done here. When the line 7 is high, then all my outputs are high. Okay. So this, whatever you can see here, it is nothing but it's a copy of your truth table. The same we have written here in the form of a case statement using the Verilog description. Okay. Finally, a default condition is very much important whenever you use the case statements. So a default condition is what? When none of these occurs. When none of these occurs, then we take them as don't care. Then the output we will be getting is don't care. Okay. So that is what we have written in your default condition. You can write your own default condition. You can either change it to high impedances or 0. No problem. Anything could be written. Okay. The case. Here it is end the case. Next end the begin. And next end your always. So all the ends. Please make sure you ended all the things, or else you will get an error. Okay. Next. Very important, friends. Here we have made a small change from the previous cases. Today we'll be writing a test bench again, no doubt, because in your syllabus they have told us to write the test bench. But one small change is what? We'll be writing the test benches using your random and tasks. In the earlier lab, we had written a test bench, but we had not used your random. Today we will use a random generation method wherein your inputs are generated randomly without you forcing them. Why we are using this method? Because there are 8 inputs. Then you can write 8 inputs, no doubt. You can write 4 inputs. But what if there are more number of inputs, like 16, like 32, like 64, like 128? Then can we sit and write the test bench considering all 128 inputs? No, friends. It becomes very hectic job. It becomes a tedious job. In order to avoid that, we have come across with the random generator. So what this random generator will do? It will randomly generate some inputs which would be used to generate the outputs. So this is the another method which I'm introducing right now. This is also correct. The earlier method is also correct. The earlier method comes into handy when you use when you have a very less amount of inputs. This method comes into handy when you have more number of inputs. Whenever there are more number of inputs, then this will be coming into handy. When there are less number of inputs, you can specify them individually. No doubt, even when there are less number of inputs, you can use the same random function. Even in that case, it is valid. But the easiest method would be specifying them individually. And when there are more number of inputs, the easiest method would be to use the random generator. Okay. So the name of my module is TB Encoder 83. Why TB? TB is nothing but test bench, Encoder 83. Then as you already know, all my inputs are written in the form of the resistors. All my outputs are written in the form of the wires. Okay. Next. So next thing is, please ignore this comment. These comments you ignore. These are these were the things which I had tried and done. So I'm just removing those comments. Fine. Okay. 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 Let us get back. So resistors and the wires are done. Resistors are nothing but your inputs. Wires are what now? Your outputs. Fine. Next. So to which module I have to club this test bench? That is written here, Encoder 83. You can observe the same module name should be here, because we are linking this present module with this test bench. So that has to be written here, the same module name. This is the instance name. Any name could be given here. No issues. Next. You should specify all the inputs and outputs. Which are my inputs now? Enable is my one input. Input IN is my another input. And OUT out is my last output. Okay. No need to mention their vector sizes here. Just mention what are my input names and what are my output names. So I hope these 3 lines are clear. Next. Similarly, we'll be writing your initial, how we had done in the previous thing. Initial, whenever you use initial, it's mandatory to use begin. So we will initialize enable equal to 0, input equal to 0. Next. This is very important, friends. Repeat 10 times. Repeat 10 times. Okay. So repeat is a keyword which will repeat this random generation somewhere around 10 times. Okay. So random generation is a function, is a task, to which inputs are what now? IN, input, and enable. Input and enable are my 2 inputs. Next, you already know what is this #45. #45 is nothing but it would be running up till 45 nanoseconds. Why nanoseconds? Because here in the time scale we have written it's nanoseconds. Okay, we have mentioned it is nanoseconds. We are using nanoseconds. You can use micro or anything else, no issues. Okay, so it would be running up till 45 nanoseconds. Fine. Next, we need to define this random generation now. we have used the function random generation, so that we will be writing as a task. That's why we have written here a test bench using random and tasks. Okay, so we will be using a task. So you can see here the task name of the task is what now? Random generation, the same name which we have used here. Okay, then output is nothing but whatever is there your output. Then your enable, finally begin $random mod of 8. So this $random mod of 8 will be generating random inputs, which would be pseudo random in nature. The random function has some logic. Don't worry about that logic. Using that logic, we are generating our inputs. Okay. Why mod 8? This is because there are 8 inputs. Okay. Next, the enable pin, directly we are using the random because there is only one enable which would be generated randomly. Okay. Finally, end this and end the task. So one task is over, the generation of the random numbers which we have used here already. So this is done. Next, we need to display we need to think about our output, how to display the values. Okay. So in order to do this, we'll be using your inputs. Inputs are what now? Enable and enable underscore t, because we are using your test bench inputs, and in underscore t and output underscore t. And then the display task remains the same as you have done in the previous lab. So this remains the same. You will be writing all your values, and you already know that the meaning of percentage B. The meaning of percentage B is nothing but it is binary. B stands for binary. Okay. And you will be displaying all the variables starting from input, that is enable, and your input in underscore t, and your output which is out underscore t. Okay. So this is done, friends. Finally, always at the output you will be displaying all your enable, input and output. So I hope so this is clear. The small change we have done in this program is we will be using the random generation, which was not used in your previous programs. Fine. So we'll save it. After saving, make sure it is in the implementation side. Do the check syntax. The other steps remains the same. There is no much difference. Then you will click on the simulation. You do the behavioral check syntax. See if there are any errors. Then you will do the behavioral model. Fine. So you can see the waves has been generated. Just click this fit to screen. Click this fit to screen. You can see various values. So the first value here you have is your enable is 0. Your enable is 0. So therefore all your outputs are 0 as well as inputs are 0. See, all these things, whatever you are seeing right now, are generated randomly by the random function. Right? We are not giving any inputs. These are generated randomly. We are giving inputs, but we are giving inputs by the random generation. Okay. Now, next thing, see here. You can observe here, the enable is high, fine. Your input is what now? It is 2. The high is 2, so therefore the output you can see here is what now? 0, 1, 0, which is 2. Okay. Now, similarly here, what happened, friends? Here, enable is high, right? Enable is high. Input is 5, but the output is don't care. Why? Because at one point it is just following your previous input. Okay. Here the problem arises whether I have to consider this, there is 0, 0, 0, 0, 1, whether I have to consider 1 or whether I have to consider 5. Due to that dilemma, here you are getting is high impedance. Okay. So you can just check here as well. The output is 0 because enable is 0, or else you would have got some output. Okay. So this is how your output would look. To make a small change, friends, we'll try with a small change. I will just increase this repeat number. I'll close the previous window. Yeah, I'll close the previous window. Again, I'll go to implementation. And I'll save it. Say check syntax again. So check syntax is done. Press at simulation, do the behavioral check syntax. Then again you do the behavioral model, simulate behavioral model. Fine. Fine. So now I have changed the time limit. Let us see if there is any change here. We have got a change here. So for 2 you have gotten value. Even for 1 you have gotten value. So if it is 1, you can just check out here. Enable is high, output is 1. So therefore you can see 0, 0, 1. So by changing those number of executions, you can see number of executions we have got is more. Why? Because we have increased the execution to 20. That is the simple reason. Okay. So this is all regarding your encoder without priority. The same thing we'll try to do with priority. So I'll just show you the code of with priority. You can observe here. So in with priority, I have just written here a small truth table. The small change here is it is 4:3. Okay. So you can extend the same thing to 8:3. I'll show it in the code. Your exercise is write this truth table as 8:3 priority encoder. You already know it. Okay. So your exercise is you should write a truth table for 8:3 priority encoder. Just check out how you would write it. From your D or HDL class, it's not a big deal. Okay, so write it. So that truth table you will be using in your program. That truth table you will be using in your program. So I have used that truth table in my program. Okay, 1 second. I am opening that project. Say open project. This is encoder 8:3 priority. Okay. So this is our 8:3 priority. So friends, here small change we have done here is it's a priority encoder. So it clearly tells us which input has to be given priority. So that is the main advantage of your priority encoder. It has tried to overcome the disadvantage of without priority encoder. So in the code as also, we'll try to check out how this could be done, how the priority could be given. Fine. So we'll start with the code now. Yeah, we'll start with the code. I hope so it's visible now. Yeah. So you can observe here, the inputs remain the same. Again, it's 8:3 itself. One small change what we have done is we have added one extra output here called as V. This V tells us whether my output is valid or not. That's why I have given it the name as V. So if the output is valid, this would be high. If the output is not valid, this would be low. That's what that is the function of your V. Remember this, friends. This is an optional. If you want, you can use it, or you can just omit it. No issues, because it's an optional pin. Even if you don't use it, there would be no issues. Okay. And finally, the output. Output is 3 bits. That's why we have written it as 0 round to T, 0 round to 2, which is 0 to 3. Next, integer. Okay. So integer you have defined I. Always add star begin. Again here we have used an active low enable. If the enable is not active, then we will put all the outputs as 0. Even the valid bit has been put to 0. So as I said, it's an optional. If you want, you can omit it. So end the if, else we'll be beginning with your block. So this is very important, friends. This change we have not seen in the without priority. So here we will be checking for your priority. Okay. So here we'll be checking for your priority, and we'll check. So it will check whether the MSB bit is active or not. If it is active, it will continue and it will break the loop. Otherwise, it will decrement and continue the same. So you can see here, if MSB bit is active, it will break the loop. If it's not active, it will continue. Okay. So we'll come to the case statements here. The case statement remains the same. Similar to your without priority. It is again the same thing. You can see when it is 001, the output is 0, and so on. Okay. So finally, you will be ending all the things. Then you will come to your test bench. So inside the test bench, again the things remain the same. You can observe here enable input, output, and on number output, which tells you whether it's valid or no. Okay. So finally, you will repeat the same thing for 25 times, and the same thing would be displayed. Okay. So we'll just check the simulation. So we'll check the simulation, friends. We'll fit it to screen. So you can see here, the enable pin is high, the output is 0010. So here, again, the 001 and your output is high. Similarly here, you can see here. Okay. So in this fashion, we'll be getting all the outputs. Okay. So if you have any doubts, please let me know. We will be happy to solve your doubts. Please don't hesitate to ask, and you can just ping us. Try to execute both the codes. Pause the video. Write down the code. Try to execute. Try to do the even the exercise what I have told, so that it would be perfect. Okay. So again, I will be meeting you in the next lab. Thank you for watching. We'll again meet in the next lab.